Look up at the night sky, and you'll see a tapestry of stars swirling into galaxies, each one a masterpiece of cosmic design. But what if I told you those spirals aren't just random? They follow the same ancient mathematical rhythm as the petals of a rose, the curve of a nautilus shell, even the arrangement of seeds in a sunflower. This isn't coincidence, it's the Fibonacci sequence, a hidden code woven into the fabric of the universe itself. Today, we're going to unravel this mystery together, tracing the golden ratio from Earth's tiniest wonders to the grandest structures in space. Think about the last time you held a pine cone or admired a sunflower. Those spirals you see aren't just beautiful, they're mathematical. The Fibonacci sequence, where each number is the sum of the two before it, creates a pattern so efficient, so universal, that nature uses it again and again. But here's the mind-blowing part. That same pattern stretches across light years, shaping the arms of spiral galaxies like our own Milky Way. How can a mathematical rule from 800 years ago describe something as vast as a galaxy? That's the question we're diving into, and the answer will change how you see the cosmos forever. This isn't just about numbers or astronomy. It's about a deeper connection between the small and the infinite. From the way plants grow to the way galaxies spin, the Fibonacci sequence is a whisper of order in what seems like chaos. By the end of this journey, you'll never look at a seashell or a starry sky the same way again. So let's step into the mystery together, decoding the universe's hidden blueprint, one spiral at a time. The Fibonacci sequence starts with 0 and 1, but what happens next is where the magic begins. Each new number is simply the sum of the two before it: 0, 1, 1, 2, 3, 5, 8, and so on, unfolding endlessly. At first glance, it might seem like just a neat mathematical trick, but plot those numbers in space, connecting them with gentle curves, and suddenly, you'll see the same elegant spiral that appears in sunflower seeds, the curl of a fern, even the swirling arms of distant galaxies. Why does this pattern show up everywhere? Nature isn't just copying homework, it's solving a problem. Think of a plant growing new leaves. If each leaf sprouted directly above the last, they'd block sunlight from one another. But by arranging them at angles dictated by the Fibonacci sequence, the plant maximizes space and light, packing each leaf into the most efficient layout possible. It's the same reason hurricanes and galaxies twist into spirals. Energy flows along the path of least resistance, and the Fibonacci spiral is nature's way of avoiding wasted effort. This isn't just about aesthetics, it's about survival. The nautilus builds its shell in a Fibonacci spiral to maintain balance as it grows, while pine cones arrange their scales in this pattern to protect seeds with perfect precision. Even our own DNA molecules twist in a double helix whose proportions echo the golden ratio, a close cousin of the Fibonacci sequence. The deeper we look, the clearer it becomes. This isn't random artistry. It's a universal blueprint, a shared language between the microscopic and the cosmic. So when we gaze at a spiral galaxy millions of light years away, we're not just seeing a random swirl of stars. We're witnessing the same mathematical elegance that shapes the world at our feet. The universe repeats its favorite patterns because they work, and the Fibonacci sequence might just be its most timeless design. Picture a whirlpool of stars, billions upon billions of them swirling together in a cosmic dance. That's the breathtaking reality of spiral galaxies, where gravity sculpts vast rivers of starlight into those iconic, sweeping arms. But here's what's truly astonishing. Those arms aren't static, unchanging structures. They're more like ripples in a pond, dynamic waves where stars drift in and out over eons, creating a pattern that mirrors the Fibonacci spiral with uncanny precision. Take the Milky Way, our galactic home. Its arms aren't rigid scaffolding but fluid, ever-shifting pathways where stars are born, live, and die. As stars orbit the galaxy's center, they don't move at the same speed. Those closer to the core race faster, while outer stars lag behind. This difference creates a natural shearing effect, stretching the galaxy's material into those graceful, spiraling arms. And just like the Fibonacci sequence in a sunflower, this spiral isn't arbitrary. It's the most efficient way for gravity to organize chaos, packing stars and gas into a structure that balances motion and stability. But why does this look so familiar? Think of water swirling down a drain or the curl of a breaking wave. These aren't just visual echoes, they're evidence of the same fundamental forces at work. Spiral galaxies, hurricanes, even the whirl of cream in your coffee all follow logarithmic spirals because physics favors efficiency. When a system rotates and contracts, the Fibonacci-like spiral emerges as the path of least resistance, the universe's way of solving a cosmic optimization problem. The deeper mystery lies in the numbers themselves. Measure the distances between a galaxy's spiral arms, and you'll often find ratios that align with the golden ratio, 1.618, the same proportion that defines the Fibonacci sequence. This isn't just poetic symmetry, it's a clue to how gravity and angular momentum interact across unimaginable scales. From the tiniest DNA helix to the grandest galaxy, the universe keeps returning to this pattern because, in a way, it's the most elegant solution to the problem of growth, motion, and structure. So when we look at a spiral galaxy, we're not just seeing a random scatter of stars. We're witnessing a universal principle in action, one that ties the smallest patterns on Earth to the grandest designs in the cosmos. The Fibonacci sequence isn't just a mathematical curiosity. It's a fingerprint of the universe's hidden order written in the stars themselves. The golden ratio is nature's favorite architect, and its fingerprints are everywhere once you know where to look. 1.618, this seemingly simple number appears in the most unexpected places, from the Parthenon's columns to the shape of a seashell. But here's what's truly fascinating. When you divide consecutive numbers in the Fibonacci sequence, like 5 by 3 or 8 by 5, the results creep closer and closer to 1.618 the further you go. This isn't just number play, it's a cosmic signature, a mathematical constant that keeps showing up in nature's most breathtaking designs. Now picture this ratio applied to something as vast as a galaxy. The spiral arms of galaxies like the whirlpool or our own Milky Way don't twist randomly. They follow angles that often match the golden ratio almost perfectly. Why? Because this angle packs stars into the most efficient arrangement possible, just like sunflower seeds are packed to maximize space. It's the universe's way of balancing expansion and structure, creating spirals that are both stable and dynamic across billions of years. But the golden ratio goes deeper than just shapes. It's tied to fundamental physics. When a galaxy rotates, its outer stars move slower than the inner ones, creating a natural shearing effect. The golden ratio emerges as the perfect compromise between these competing forces, allowing the spiral to maintain its form while stars drift in and out of its arms. It's the same reason hurricanes and nautilus shells share this spiral. Fluids and growth patterns naturally settle into this ratio because it minimizes energy waste. What's even more astonishing is how this ratio bridges art and science. Renaissance painters like Da Vinci used the golden ratio to compose visually harmonious paintings. while ancient Greek architects built temples with these proportions because they felt inherently pleasing. Today, we find the same ratio in everything from DNA molecules to the branching of trees. The universe seems to whisper the same number whether it's building a galaxy or a fern frond, proving that beauty isn't just in the eye of the beholder, it's written into the fabric of reality itself. So the next time you see a spiral weather in a galaxy photo or a pine cone, remember you're glimpsing a universal language. The golden ratio isn't just about math or aesthetics. It's a clue to how the cosmos balances chaos and order, growth and stability. From the smallest leaf to the grandest galaxy, this proportion is nature's way of saying, "This works, let's use it everywhere." Open a sunflower, and you'll find a hidden universe in its center, hundreds of tiny seeds curling away from each other in perfect spirals, some clockwise, others counterclockwise. Count those spirals and you'll almost always land on consecutive Fibonacci numbers, 21 and 34, or 34 and 55. This isn't just a quirk of sunflowers, it's a survival strategy so effective, plants have been using it for millions of years. They're solving the same problem galaxies face: how to pack the most material into the least space without crowding or waste. This phenomenon, called Philotaxis, is nature's way of optimizing growth. Take a pineapple with its hexagonal scales spiraling around its body in interlocking helices, or a succulent, its plump leaves unfolding in a spiral staircase to catch sunlight from every angle. Each of these plants is following a mathematical playbook written in the Fibonacci sequence, arranging their structures at precise angles around 137.5 degrees apart to avoid overlap and maximize exposure. It's no accident this angle matches the golden ratio's mathematical signature. When every degree counts, evolution converges on the most efficient solution. Now zoom out to a spiral galaxy. Those vast, swirling arms aren't so different from a sunflower's seeds. Stars and gas clouds are spaced along logarithmic spirals, their positions dictated by gravity's version of the same optimization problem. Just as leaves avoid shading each other, stars in a galaxy's arms avoid crowding too densely, finding equilibrium between motion and structure. The result: a pattern eerily reminiscent of the Fibonacci spirals in your backyard garden. Could it be that galaxies and plants are whispering the same mathematical secret? Both are systems where growth meets rotation, where efficiency dictates form. A plant spiral ensures every leaf gets its share of light. A galaxy spiral ensures stars distribute their orbits sustainably. One unfolds in millimeters, the other across light years, yet both speak the language of the golden ratio. This isn't mere coincidence, it's evidence of a deeper truth. The universe has a favorite blueprint, and whether it's building a daisy or a galaxy, it reaches for the same timeless tools. So the next time you slice a pineapple or gaze at a Hubble image of the Whirlpool galaxy, remember, you're seeing two versions of the same cosmic rhythm. From the tiniest shoot to the grandest stellar dance, the Fibonacci sequence is the universe's way of saying, "This works, let's use it everywhere." Logarithmic spirals are nature's way of balancing growth and proportion, a shape so versatile it appears in everything from the tiniest seashell to the grandest galaxy. Unlike the rigid, evenly spaced coils of an Archimedean spiral, a logarithmic spiral expands outward while keeping its angles perfectly consistent, like a cosmic blueprint that scales effortlessly from the microscopic to the astronomical. Take the Nautilus shell, for instance. Each chamber grows larger than the last, yet the curve remains flawlessly smooth, following the exact same mathematical rhythm. This isn't just a pretty design, it's a masterclass in efficiency, allowing the creature inside to expand without ever outgrowing its home. Now, imagine that same principle applied to something as powerful as a hurricane. The storm's swirling arms don't tighten or fray as they spin. They maintain a steady, logarithmic spiral, channeling wind and energy along the most fluid path possible. Even the whirlpool in your bathtub drains in this same elegant curve because when fluids move under rotation, they naturally settle into this shape. It's the universe's default setting for systems that grow while turning, a geometric cheat code for stability in motion. But here's where it gets cosmic. Spiral galaxies, like the iconic Whirlpool Galaxy, don't just resemble hurricanes or nautilus shells by accident. Their arms are logarithmic spirals too, sculpted by gravity and momentum into curves that echo the golden ratio. Stars aren't fixed in these arms like beads on a string. They drift in and out, tracing orbits that create the illusion of a spinning pattern. And just like the nautilus, the galaxy's spiral widens as it stretches outward, maintaining that perfect, consistent angle across thousands of light years. Why does this shape keep appearing across such wildly different scales? The answer lies in the math behind growth. Logarithmic spirals emerge whenever a system expands while rotating, whether it's a plant adding new leaves or a galaxy stretching with the universe itself. The Fibonacci sequence codifies this pattern, generating spirals where each turn is precisely 1.618 times wider than the last, the golden ratio in action. It's a universal solution to a universal problem: how to grow without losing form, how to move without breaking apart. So whether you're studying the curve of a fern or the sweep of a distant galaxy, you're seeing the same geometric wisdom at work. Logarithmic spirals aren't just nature's favorite shape. They're proof that the universe speaks a common language, one where growth, motion, and beauty are all written in the same elegant equation. Imagine a crowded highway where cars slow down, bunching up into clusters before speeding away again. Only this highway is made of stars, and the traffic jam lasts for millions of years. That's essentially what's happening in the spiral arms of galaxies like our Milky Way. These iconic swirls aren't permanent structures but dynamic density waves, rippling through the galactic disk like sound waves through air. As stars and gas clouds move through these regions of higher density, they slow down, compressing like cars in a cosmic bottleneck. This compression triggers bursts of star formation, lighting up the arms with young, brilliant stars that make the spiral pattern visible across the void of space. The magic lies in how these waves propagate. Unlike a rigid spiral drawn on paper, the stars themselves don't stay locked in the arms forever. They drift in and out over time while the wave pattern, the spiral, moves independently like a ripple in a pond that keeps its shape even as water molecules pass through it. This explains why spiral arms don't wind up tighter and tighter as the galaxy rotates. The wave maintains its structure, a self-reinforcing pattern where gravity, rotation, and star formation work in concert. Here's where the Fibonacci connection deepens. The spacing between these density waves often follows ratios eerily close to the golden ratio, the same proportion that governs the Fibonacci sequence. As gas clouds compress in the wave, they fragment into clumps that form stars at intervals mirroring this mathematical harmony. It's as if the galaxy is solving a puzzle, balancing the pull of gravity against the centrifugal force of rotation. And the Fibonacci spiral emerges as the most stable, energy-efficient solution. Think of it like a grand cosmic dance. Gravity pulls matter together while the galaxy's rotation tries to fling it apart. The density wave is the compromise, a rhythmic pattern where star formation and motion synchronize. Even the distribution of newborn stars within the arms often follows Fibonacci-like spacing, clustering in ways that maximize stability. From the microscopic arrangement of leaves to the colossal architecture of galaxies, Nature defaults to this pattern because it's the ultimate balancing act, a recipe for growth without chaos, motion without collapse. So when we admire a spiral galaxy's graceful arms, we're not just seeing a static snapshot. We're witnessing a living, breathing process, a wave of creation that sculpts stars and shapes worlds, all while whispering the universe's favorite mathematical secret. The Fibonacci sequence isn't just a curiosity, it's the rhythm of the cosmos itself, written in the stars. To truly understand why galaxies embrace the Fibonacci spiral, we need to step inside the virtual laboratories of astrophysicists. Imagine a supercomputer humming with the power of thousands of processors, crunching numbers to simulate the birth and evolution of a galaxy over billions of years. These aren't just pretty animations, they're precise mathematical models where every star, every wisp of gas obeys the unbreakable laws of physics. And when these digital galaxies finally take shape, something remarkable happens. Their spiral arms don't form randomly, they twist into patterns that mirror the Fibonacci sequence with startling accuracy, as if the universe itself is running the same code across cosmic scales. These simulations reveal a cosmic dance of gravity and motion. As virtual gas clouds collapse under their own weight, they begin to spin, flattening into disks like pizza dough tossed into the air. Angular momentum, the same force that keeps a figure skater spinning faster as they pull their arms in, shapes these disks into spirals. But here's the breakthrough: the exact angles of those spirals often align with the golden ratio. When researchers tweak the variables adjusting the galaxy's mass, rotation speed, or gas density, the Fibonacci-like spirals persist, emerging as a natural solution to the equations governing cosmic structure. One groundbreaking simulation, called the Millennium Run, tracked over 10 billion virtual particles to model the universe's evolution. In countless trials, spiral galaxies consistently self-organized into arms whose spacing and curvature echoed logarithmic spirals, the same geometric family as Fibonacci's sequence. This wasn't programmed into the simulation. It arose organically from the interplay of gravity, centrifugal force, and turbulence. Like a river carving the most efficient path downhill, the galaxy's structure found equilibrium in a spiral that balances expansion and cohesion. What's even more compelling is how these virtual galaxies solve the winding problem. In the early 20th century, astronomers worried that if spiral arms were fixed structures, they'd wind themselves into a tight knot after a few rotations. But simulations show the arms are density waves, regions where stars and gas pile up like cars in a slowdown, creating bright, transient patterns. Stars pass through these waves, but the spiral itself endures, maintaining its shape over eons. And the spacing between these waves, often a near-perfect golden ratio, allowing the galaxy to sustain its elegant form without collapsing or flying apart. These digital experiments don't just replicate nature, they help decode it. When a simulated galaxy's spiral arms match Hubble images of real ones down to the finest details, it's a clue that the Fibonacci sequence isn't a coincidence, it's a mathematical inevitability. From the whirl of a galaxy to the curl of a fern, the universe keeps returning to this pattern because, in the grand equation of existence, it's the most elegant way to grow, move, and endure. At the heart of most spiral galaxies, including our own Milky Way, lurks an invisible monster, a supermassive black hole with gravity so intense, not even light can escape. But these cosmic behemoths aren't just destructive forces. They may actually be the unseen sculptors of the galaxy's iconic spiral arms. Picture a black hole's gravitational pull like an invisible hand gently tugging at the fabric of space itself, warping the orbits of nearby stars and gas clouds. Over millions of years, these subtle disturbances ripple outward, organizing the chaos into coherent spiral patterns like a stone dropped in a pond, but with consequences that shape an entire galaxy. Take the black hole at the center of the Andromeda Galaxy, our nearest galactic neighbor. With a mass equivalent to 100 million suns, its gravity subtly herds stars into the sweeping arms we see from Earth. Computer models show how these black holes don't just sit idle, they actively funnel gas and dust into their accretion disks, creating swirling maelstroms of superheated material. And here's where it gets eerie. Some of these disks spiral inward with a curvature that mirrors the Fibonacci sequence, as if the black hole is drawing energy in nature's preferred mathematical language. This connection goes beyond mere geometry. When black holes feed, they unleash torrents of energy in the form of jets and radiation, which can compress surrounding gas clouds and trigger waves of star formation. These newborn stars, glowing bright and blue, trace out the galaxy's spiral arms like cosmic streetlights. In essence, the black hole isn't just shaping the galaxy's structure, it's also lighting it up from within, threading the spiral with stellar nurseries that follow the same mathematical rhythms as a nautilus shell or a sunflower seed. Yet the most tantalizing clue lies in the accretion disks themselves. Recent observations of quasars, supermassive black holes in distant galaxies, reveal that their disks sometimes spiral inward at angles matching the golden ratio. Matter doesn't fall in haphazardly. It follows an orderly, Fibonacci-like path as it's devoured. This suggests that the same mathematical principles governing growth on Earth might also dictate how black holes consume and reshape their surroundings, bridging the microscopic and the cosmic once again. So when we gaze at a spiral galaxy, we're not just seeing stars and gas, we're witnessing the aftermath of a delicate gravitational ballet, where a black hole's silent influence weaves order from chaos. From the whirl of its accretion disk to the grand sweep of galactic arms, the universe keeps returning to the same elegant patterns, proving that even the darkest corners of space obey nature's timeless mathematical rules. The ancient Greeks called it the divine proportion, a sacred ratio so perfect they believed it could unlock the mysteries of beauty and the cosmos. Walk through the Parthenon's ruins today, and you'll find its columns spaced according to the golden ratio, its triangular pediments precisely 1.618 times wider than they are tall. But this wasn't just architectural flair, it was a deliberate echo of patterns they saw in the natural world, from the curl of a ram's horn to the spiraling stars above. Pythagoras and his followers worshipped numbers as the language of the gods, convinced that mathematical harmony underpinned everything from music to the motions of planets. Centuries earlier, the Egyptians encoded the same ratio into the Great Pyramid of Giza. The slope of its sides, the dimensions of its chambers all align with Fibonacci-like precision. Some scholars argue this wasn't accidental. The pyramid's architects may have been mirroring celestial patterns observed over generations. A surviving papyrus from the time of Pharaoh Amenem, Hat III, shows spiral diagrams strikingly similar to modern renderings of galaxy arms, suggesting ancient skywatchers saw more than random starlight. They may have recognized an order modern science is only now quantifying. Halfway across the world, Hindu temple builders constructed mandalas with spiraling geometries that precisely match logarithmic curves. The Sri Yantra, an ancient meditation diagram, interlaces 9 triangles to form 43 smaller triangles, a fractal arrangement that naturally approximates the golden ratio. These weren't just artistic choices, they were attempts to model cosmic energy flows, to build bridges between earthly structures and the mathematical fabric of the universe. Even more compelling are the celestial maps left by the Maya, whose astronomers tracked Venus cycles with jaw-dropping accuracy. Their Dresden Codex contains spiral glyphs that some researchers interpret as early depictions of galactic rotation. While we can't know their full intent, the parallel is haunting. Civilizations separated by oceans and millennia independently gravitated toward spiral symbolism when describing the heavens. Whether through intuition or meticulous observation, they sensed a truth we now confirm with supercomputers, that the same mathematical threads weave through seashells, temples, and swirling galaxies alike. What did these cultures know that took modern science millennia to rediscover? Perhaps they understood something we've since forgotten, that beauty and function aren't separate ideals but two expressions of the same universal code. When an Egyptian architect squared a pyramid or a Greek sculptor shaped marble, they weren't just creating art, they were participating in a cosmic pattern, aligning human craftsmanship with the same rhythms that spin stars into spirals and leaves into perfect Fibonacci curves. Spiral galaxies may be the most famous cosmic structures shaped by the Fibonacci sequence, but they're far from alone. Look closely at a planetary nebula like the Helix Nebula, and you'll see delicate tendrils of gas curling outward in logarithmic spirals, the same graceful curves found in a chambered nautilus. When aging stars shed their outer layers, the ejected material doesn't just expand randomly. It often twists into intricate patterns where the spacing between spiral features mirrors Fibonacci ratios. This happens because the dying star's rotation interacts with its expanding shell, creating shock waves that organize the chaos into mathematically harmonious forms. Even before stars die, their birth tells a similar story. Protoplanetary disks, those swirling platters of dust and gas where planets form, frequently exhibit spiral arms with spacing that follows the golden ratio. The young star HL Tauri, located 450 light-years away, shows this beautifully in radio telescope images. Its disk contains dark gaps where infant planets are carving paths, but between those gaps, bright spiral arms coil outward at angles matching 1.618. This isn't just celestial decoration, it's evidence of density waves moving through the disk, guiding material into orbits that naturally settle into Fibonacci-like arrangements. The same physics that arranges seeds in a sunflower seems to be at work here, sculpting baby solar systems millions of miles across. Zoom out further, and the pattern persists on the grandest scales imaginable. The large-scale structure of the universe, those vast cosmic webs of galaxy clusters and filaments, reveals a startling fractal quality when mapped in 3 dimensions. While not perfect spirals, these filaments branch and twist in ways that statistically align with Fibonacci-inspired growth patterns. Computer simulations of the early universe show how tiny quantum fluctuations grew under gravity's influence, stretching into tendrils whose proportions often approximate the golden ratio. It's as if the universe, from its very first moments, carried the seeds of this mathematical harmony, letting it unfold from quantum scales to galactic superclusters. Why does this pattern appear across such different phenomena? The answer lies in optimization. Whether it's gas swirling around a newborn star, debris expanding from a dying one, or galaxies clustering along invisible threads, nature favors arrangements that balance competing forces efficiently. Spiral structures allow rotating systems to redistribute angular momentum, while Fibonacci-like spacing prevents overcrowding, just like trees branching to avoid shading their own leaves. The universe, it seems, has a limited toolkit of solutions, and when rotation meets expansion, the golden ratio often emerges as the most stable configuration. This cosmic ubiquity challenges our notions of scale. A nebula's delicate swirls and the universe's colossal filaments may differ in size by countless orders of magnitude, but they speak the same mathematical language. From the whirl of an atom to the spin of a galaxy cluster, the Fibonacci sequence appears wherever growth and motion intertwine, proof that the universe's blueprints come in recursive, self-similar designs. The next time you see a spiral weather in a pine cone or a Hubble image, remember you're glimpsing a universal principle, one that stitches the cosmos together from the smallest shell to the grandest web of galaxies. We think of galaxies as dazzling rivers of stars, but what we see is only a fraction of the story. Surrounding every spiral galaxy like our Milky Way is an enormous, invisible halo of dark matter, a mysterious substance that doesn't emit light but exerts a gravitational pull so strong it sculpts the very fabric of the cosmos. Without these unseen halos, galaxies would fly apart, their stars scattering into the void. But here's the twist: dark matter might do more than just hold galaxies together. It could be the hidden choreographer behind their Fibonacci perfect spirals, subtly guiding visible matter into those mesmerizing logarithmic curves. Picture a galaxy as a grand cosmic puppet show. The stars and gas we observe are the marionettes dancing across the stage, but dark matter is the puppeteer, its gravitational strings dictating the performance. Computer simulations reveal how dark matter halos create a gravitational scaffold, shaping the rotation of galactic disks. As ordinary matter orbits within this invisible framework, it naturally settles into density waves, those spiral arms where stars are born. And just like the seeds in a sunflower, the spacing between these arms often aligns with the golden ratio, as if dark matter's influence nudges them into nature's favorite mathematical arrangement. Some astrophysicists take this idea even further. They propose that dark matter doesn't just provide a static backdrop, but actively interacts with spiral structure through dynamic feedback loops. Imagine tossing pebbles into a pond. Each ripple affects the next. Similarly, as stars form in spiral arms, their explosions supernova pump energy back into the surrounding gas, creating shock waves. Dark matter's gravity may then amplify these waves, reinforcing the spiral pattern in a self-perpetuating cycle. This could explain why Fibonacci-like spirals persist for billions of years, even as stars constantly drift in and out of the arms. Yet the most tantalizing clue comes from galaxies that defy expectations. Take the ultra-diffuse galaxy Dragonfly 44, which emits almost no light yet contains a halo of dark matter rivaling the Milky Ways. Despite its faint appearance, this ghostly galaxy rotates with the same orderly precision as its brighter counterparts, suggesting dark matter's gravitational influence is the true architect of cosmic structure. If invisible halos can sculpt rotation curves so precisely, why couldn't they also fine-tune the angles of spiral arms? Of course, not all galaxies fit this mold. Some exhibit irregular, chaotic shapes, often the result of collisions or insufficient dark matter. But even in these cases, when spiral structure does emerge, it frequently follows the same mathematical cadence. This consistency hints at a universal rulebook where dark matter sets the stage, and visible matter arranges itself according to timeless geometric principles. So the next time you marvel at a galaxy's spiral, remember, you're seeing only the illuminated fraction of a far grander design. The Fibonacci sequence in those sweeping arms might be nature's signature, but dark matter could well be the hand that guides the pen, writing the universe's hidden equations in the spaces between the stars. At the subatomic level, where particles flicker in and out of existence like cosmic fireflies, nature's love for the Fibonacci sequence takes on an even more mysterious form. Certain quantum materials like quasi-crystals, which defy traditional symmetry, arrange their atoms in patterns that echo the Fibonacci sequence with uncanny precision. These aren't just random arrangements. They're mathematical masterpieces where atoms align in ratios mirroring the golden spiral, creating structures so orderly they once baffled scientists. When researchers first discovered quasi-crystals in the 1980s, their atomic lattices displayed five-fold symmetry, something once thought impossible in nature. Yet there it was, a microscopic echo of the same spirals we see in galaxies and sunflowers. How does this quantum choreography connect to the grand spirals of galaxies? The bridge might lie in something called the quantum Fibonacci chain, a theoretical model where particles interact in ways that produce Fibonacci-like sequences. Imagine electrons hopping along a one-dimensional path, their positions dictated by quantum rules, yet somehow, their most stable configurations often settle into patterns that resemble the Fibonacci sequence. This isn't just abstract math, it's been observed in lab-grown materials like graphene, where electrons under extreme conditions form fractal patterns eerily reminiscent of galactic arms. It's as if the universe uses the same mathematical toolkit, whether it's arranging electrons or sculpting stars. But here's where it gets truly mind-bending. Some physicists speculate that these quantum patterns could scale up through a phenomenon known as emergence, where simple rules at the smallest levels give rise to complex behaviors at larger scales. Think of how individual water molecules, each following basic physics, collectively create the intricate whirl of a hurricane. In the same way, quantum fluctuations in the early universe might have seeded density variations that later grew into galactic spirals. The Fibonacci sequence could be the thread stitching these scales together, a hidden algorithm running from the quantum foam to the cosmic web. Yet the most compelling evidence comes from black holes, those cosmic maelstroms where quantum mechanics and gravity collide. Recent studies of black hole entropy, a measure of their internal chaos, reveal patterns that align with Fibonacci numbers. The way information scrambles at a black hole's event horizon, the way energy dissipates, even the way space-time itself warps near these objects, all hint at mathematical harmonies that resonate with the golden ratio. If black holes, the most extreme objects in the universe, obey these rules, could it be that the Fibonacci sequence is woven into the fabric of spacetime itself? This isn't just poetic symmetry, it's a frontier of modern physics. String theory, for instance, suggests that the universe's fundamental particles might vibrate in dimensions curled up at scales far smaller than an atom, and some of these vibrational modes correspond to Fibonacci-like sequences. Even the branching paths of quantum particles in double-slit experiments sometimes trace probabilities that cluster around golden ratios. The deeper we probe, the more it seems that nature's blueprint doesn't just repeat across scales, it's fundamentally encoded in the quantum realm, whispering its patterns upward into the cosmos. So when we marvel at a spiral galaxy, we might actually be seeing the shadow of quantum mechanics writ large. From the dance of electrons to the swirl of stars, the universe keeps returning to the same elegant solutions, not because it's copying itself, but because these patterns represent the most stable, efficient ways for energy and matter to organize. Whether at the Planck scale or across megaparsecs, the Fibonacci sequence emerges as a universal constant, a silent conductor orchestrating the symphony of existence from the infinitesimal to the infinite. Chaos and order aren't opposites, they're partners in an eternal cosmic dance. Take a handful of sand and let it trickle through your fingers. Each grain follows a simple path dictated by gravity, yet the pile that forms at your feet is a masterpiece of unpredictability, its slopes and ridges impossible to forecast. This is chaos theory in action, the idea that even the simplest rules can birth breathtaking complexity. Now imagine that same principle unfolding across a galaxy, where billions of stars and swirling gas clouds interact under gravity's unyielding pull. The result, spiral arms so precise they mirror the Fibonacci sequence order emerging effortlessly from what should be chaos. At first glance, a galaxy seems like the last place you'd find mathematical harmony. Stars collide, supernova explode, and gas clouds fragment into turbulent vortices. Yet somehow, amid this pandemonium, spiral patterns emerge with near-perfect logarithmic curves. The secret lies in what scientists call deterministic chaos, systems where tiny, unpredictable fluctuations lead to large-scale order. Picture a leaf floating down a river. Its exact path is chaotic, buffeted by invisible currents and eddies, but the river itself flows in a predictable direction. Similarly, while we can't track every star in a galaxy, their collective motion settles into spirals because the underlying physics, gravity, and angular momentum favor this arrangement. It's not despite the chaos, but because of it that galaxies find their Fibonacci-inspired form. This phenomenon isn't unique to space. Look at Earth's weather systems, where tiny changes in air pressure can spark hurricanes that spiral with Fibonacci-like precision. Or consider the human heart, where seemingly erratic electrical pulses organize into the steady rhythm that keeps us alive. In each case, chaos doesn't lead to disorder but to a higher kind of order, one that balances flexibility and stability. Galaxies are no different. Their spiral arms aren't rigid structures but dynamic patterns, constantly reshaped by the very turbulence that might seem to threaten them. The deeper truth here is that nature has a limited palette of stable solutions. When a system rotates and grows, whether it's a galaxy, a hurricane, or a nautilus shell, the Fibonacci spiral emerges as the most energy-efficient way to balance expansion and cohesion. Chaos doesn't erase this tendency. It refines it, like a sculptor chiseling away excess marble to reveal the statue within. Supercomputer simulations of galaxy formation show this vividly. Even when researchers start with random distributions of gas and stars, the simulated galaxies inevitably develop spiral arms whose angles and spacing converge toward the golden ratio. The universe, it seems, has a favorite shape, and chaos is just the tool it uses to carve it. So the next time you see a spiral weather in a galaxy or a seashell, remember you're witnessing chaos and order in collaboration. The Fibonacci sequence isn't imposed from above but bubbles up from below, a natural consequence of simple rules playing out across unimaginable scales. From the quantum realm to the cosmic web, the universe keeps returning to this pattern not because it's planned but because, in the grand equation of existence, it's the most elegant way to dance on the edge between randomness and rhythm. Leonardo da Vinci's sketchbooks are filled with spiral studies of whirlpools, flowing water, even the curls of human hair. But one sketch stands out, his famous Vitruvian Man, where a perfectly proportioned figure stretches within a circle and square. The distances between the man's limbs, the placement of his navel, all align with the golden ratio, a mathematical harmony Da Vinci believed reflected the divine blueprint of nature. What he couldn't have known is that same ratio was shaping galaxies millions of light years away, their spiral arms curling with the same precision as the waves in his drawings. For Da Vinci, art wasn't just about beauty. It was a way to decode the hidden order of the world, a quest that modern astrophotographers continue today with telescopes instead of paintbrushes. Centuries later, Salvador Dali took this obsession further. His surreal masterpiece, The Sacrament of the Last Supper, frames Christ and the disciples inside a hovering dodecahedron, a shape whose angles and proportions hum with golden ratio harmonies. Dali didn't just use the ratio for aesthetics, he believed it tapped into cosmic truths. In a twist he'd have adored, we now know that same geometry appears in quasicrystals, materials where atoms arrange in Fibonacci-like patterns that defy classical symmetry. Dali's art, like the universe itself, thrived where rigid rules bent into something more mysterious. Fast forward to today, and the marriage of art and astrophysics has never been more vivid. Astrophotographers like Robert Gendler and Judy Schmidt use Hubble and Webb telescope data to craft images of galaxies so stunning they belong in galleries. But these aren't just pretty pictures, they're scientific revelations. When Gendler processed an image of the Whirlpool galaxy, he highlighted spiral arms whose curvature matched the golden ratio to within a fraction of a degree. The same mathematical grace Da Vinci chased in human anatomy was etched across a cosmic canvas 50 million light-years wide. This synergy goes deeper than inspiration. Algorithms now analyze galaxy shapes using the golden ratio as a template, helping astronomers classify structures too complex for the human eye to parse. Meanwhile, artists like Katie Patterson embed Fibonacci sequences into installations, mapping stellar patterns onto piano strings or weaving cosmic dust into tapestries. These projects aren't metaphors, they're bridges showing how creativity and cosmology spring from the same source, a universe that favors spirals, whether in brushstrokes or starlight. Perhaps the most poetic proof lies in the pillars of creation, those towering columns of gas where stars are born. When NASA released Webb's near-infrared image, the public gasped at its ethereal beauty, but mathematicians noticed something else. The pillars' branching filaments followed Fibonacci like fractals, echoing the growth patterns of trees and rivers. Here, in the cradle of creation itself, art and science collapse into a single truth: the universe doesn't just contain beauty. It is beauty, written in a language we're only beginning to understand, one where a 15th century sketch and a 21st century telescope reveal the same eternal spiral. Claude Debussy's Clair de Lune doesn't just ripple like moonlight on water. It unfolds like a Fibonacci spiral in sound. The French composer, obsessed with nature's patterns, structured entire passages around the golden ratio, placing crescendos and key changes at precise mathematical intervals. In La Mer, the ebb and flow of the orchestra mirrors the logarithmic swell of ocean waves, each musical phrase expanding 1.618 times longer than the last. This wasn't arbitrary. Debussy believed music should echo the world's hidden geometry, and modern acoustics proves he was onto something. When sound waves travel through air, they don't just move in straight lines, they curl into intricate spirals, especially in reverberant spaces like cathedrals or canyon walls. Record these spirals on a spectrogram, and you'll see patterns eerily reminiscent of galaxy arms, a cosmic duet between physics and harmony. The connection runs deeper than metaphor. Take the grand pipe organs of Europe, where air forced through columns creates standing waves that resonate at Fibonacci-like frequencies. The pipe's lengths often follow golden ratio proportions, producing chords that feel inherently balanced to the human ear. Even the cochlea in our inner ear, a spiral-shaped organ, processes sound in logarithmic steps, with hair cells spaced like seeds in a sunflower. It's as if our very biology is tuned to Fibonacci's mathematical melody. This symphony of structure extends to modern music too. Tool's Lateralis famously arranged its lyrics in Fibonacci syllables, while Björk's Biophilia album mapped musical scales to DNA sequences. But perhaps the most striking parallel lies in cymatics, the study of visible sound. When sand or water is vibrated at specific frequencies, the particles self-organize into spiraling patterns that mirror galactic arms. A low C note might scatter grains into a simple circle, but raise the pitch, and suddenly you'll see intricate walls with Fibonacci spacing, proof that sound and shape share a universal language. Why does this resonance exist? Just as density waves shape galaxies by organizing stars, sound waves organize energy into coherent forms. A vibrating violin string doesn't just produce one note, it generates harmonics, higher-pitched tones whose frequencies align with whole number ratios. These harmonics create the richness we perceive as musical texture, much like how overlapping density waves give galaxies their layered spiral structure. The golden ratio emerges as the most irrational number, meaning it's the hardest to approximate with simple fractions. In music, this translates to progressions that feel endlessly fresh, avoiding the monotony of predictable repetition. From the spiral grooves of vinyl records to the fractal algorithms generating electronic music today, the Fibonacci sequence hums beneath the surface of every note. When we listen to a symphony or gaze at a spiral galaxy, we're not just perceiving beauty, we're sensing the quiet persistence of a pattern that binds the cosmos together, one vibration at a time. Fractals are nature's hall of mirrors, patterns that repeat themselves endlessly, no matter how far you zoom in or out. Take a fern frond, for example. Each leaf is made up of smaller leaflets, which in turn are composed of even tinier lobes, all arranged in a Fibonacci-inspired spiral. This self-similarity isn't just a quirk of botany. It's a fundamental blueprint that stretches from the veins of a leaf to the branching arms of galaxy clusters. The universe, it seems, adores repetition with a twist, crafting intricate designs that echo across unimaginable scales. Coastlines offer another stunning example. From space, the jagged edge of a continent might look like a single, rough curve, but zoom in and you'll find bays within bays, cliffs within cliffs, each segment a smaller version of the whole. Measure the length of a coastline with increasing precision, and it grows endlessly, defying traditional geometry. This fractal quality isn't just a measurement puzzle, it's a clue to how nature builds complexity from simplicity. The same recursive rules that shape a pebble's erosion also sculpt the vast, winding rivers of interstellar gas in the Eagle Nebula. Now cast your gaze upward to the cosmos. Galaxy clusters, those sprawling metropolises of stars, often arrange themselves in fractal-like networks. The distribution of matter isn't random. It forms filaments and voids that repeat their patterns whether you're observing a region 10 million light-years wide or a slice just a fraction of that size. This cosmic web, as astronomers call it, mirrors the branching of trees or the human circulatory system, structures where efficiency demands repetition at every scale. Even the distribution of dark matter, invisible yet omnipresent, follows these recursive rules, weaving an unseen fractal tapestry that holds the universe together. What's truly mind-bending is how these patterns emerge from pure mathematics. The Mandelbrot set, a fractal generated by a single equation, produces infinite complexity from a simple feedback loop. Take a number, square it, add a constant, and repeat. The resulting shapes, whirling spirals, branching tendrils look unnervingly like celestial formations or biological growths. It's as if the universe is running the same code everywhere, from the flicker of quantum particles to the slow dance of superclusters. This self-similarity suggests something profound. The laws governing the very small and the unimaginably vast might not be so different after all. A neuron's branching dendrites resemble the universe's large-scale structure, not by coincidence but because both systems optimize for connectivity and efficiency. The Fibonacci sequence, with its recursive growth, becomes the perfect tool for this universal engineering, ensuring stability whether it's arranging petals on a flower or stars in a galactic arm. So the next time you trace the spiral of a pine cone or lose yourself in a Hubble image of the Veil Nebula, remember, you're glimpsing the same mathematical heartbeat. Fractals aren't just patterns, they're a language, one that nature speaks fluently from the infinitesimal to the infinite. And in their endless repetition, they whisper a secret. The universe, for all its grandeur, is built on rhythms we're only beginning to decode. Human eyes lock onto spirals with an almost magnetic pull, whether it's the hypnotic swirl of a Van Gogh painting or the cosmic whirl of a galaxy in a telescope image. This instinctive attraction isn't random, it's etched into our biology. Neuroscientists have discovered that when we view Fibonacci spirals, the visual cortex lights up with activity, processing these shapes faster and more pleasurably than jagged or chaotic patterns. It's as if our brains have a built-in appreciation for this specific curve, recognizing it as a signal of harmony and efficiency. This preference might trace back to our earliest ancestors. Imagine a hunter-gatherer scanning the savannah. Spotting a spiral seashell or the coiled thread of a snake meant the difference between survival and danger. Over millennia, our visual system evolved to prioritize these patterns, wiring us to find them not just noticeable but inherently satisfying. Modern studies support this. When shown a series of shapes, people consistently rate golden ratio spirals as most beautiful, even if they've never heard of Fibonacci. The response is immediate and emotional, like hearing a familiar melody. Artists and architects have exploited this instinct for centuries, from the spiraling staircases of Renaissance castles to the logarithmic curves of Frank Lloyd Wright's Guggenheim Museum. Designs that mimic nature's ratios feel intuitively right. Even infant studies reveal babies stare longer at Fibonacci-inspired mobiles than at irregular ones, suggesting this preference is hardwired, not learned. The spiral becomes a universal language of aesthetic pleasure, transcending culture and era. Now consider how this plays out when we gaze at galactic images. Hubble's portraits of whirlpool galaxies trigger the same neural applause as a blooming rose or a nautilus shell, because they're all variations on nature's most efficient theme. Astrophotographers often frame these images to emphasize their logarithmic curves, knowing viewers will feel their pull at a visceral level. It's no coincidence that some of the most shared astronomy photos feature galaxies like Messier 74, nicknamed the Phantom Galaxy, whose arms coil with Fibonacci precision. Our brains don't just see beauty in these spirals, they read them as cosmic affirmations of order, but the fascination goes deeper than mere recognition. Psychologists suggest spirals captivate us because they represent growth and journey, a visual metaphor for life's unfolding. Every rotation of a galactic arm mirrors the way ferns unfurl or hurricanes gather strength, tapping into our subconscious awe for systems that balance dynamism and stability. When we lose ourselves in a spiral, whether in art or astronomy, we're not just admiring a shape. We're glimpsing a pattern that feels strangely like home, a silent echo of the rhythms that shaped our minds and the universe alike. DNA doesn't just carry our genetic code, it twists it into a spiral staircase, with each rung spaced according to proportions that would make Fibonacci smile. The famous double helix wins at an angle of 34 degrees, a number straight from the heart of the sequence. But this isn't just elegant geometry. It's a clue that life might be written in the same mathematical language as the cosmos. From the microscopic coils of proteins to the vast arms of galaxies, nature keeps returning to this spiral blueprint, as if whispering a secret about how growth and structure intertwine across every scale. Consider the cochlea in your inner ear, a seashell-shaped organ so perfectly coiled that it mimics the logarithmic spirals of distant nebulae. This isn't artistic coincidence, it's physics in action. The cochlea's spiral design allows it to sort sound frequencies with breathtaking efficiency, much like a galaxy's arms sort stars by age and density. Even your fingertips bear this cosmic signature. Fingerprints loop and wall in patterns that, when analyzed, often align with Fibonacci-inspired fractals. These ridges aren't random, they maximize tactile sensitivity, proving once again that nature defaults to spirals when precision matters most. The connection goes deeper than anatomy. During embryonic development, cells divide and migrate in spiraling motions, following chemical gradients that resemble the density waves shaping galactic arms. Plants do the same. Their roots spiral downward as they grow, tracing paths through soil that mirror the orbits of stars around a galaxy's core. This parallel isn't poetic license. It's a testament to how universal principles manifest whether you're building a fern or a solar system. Could it be that life evolved these patterns because the universe itself is built on them? Quantum physics hints at this possibility. The way electrons orbit atomic nuclei, jumping between energy levels in discrete steps, echoes the integer leaps of the Fibonacci sequence. Even the branching of neurons in your brain follows fractal patterns seen in cosmic webs, suggesting that consciousness itself might be shaped by the same forces that arrange stars. From the helix of a DNA strand to the spiral of a hurricane, from the curl of a fiddlehead fern to the whirl of a galaxy, the message is clear. Life doesn't just exist in the universe, it dances to its rhythm. The Fibonacci sequence isn't merely a mathematical curiosity. It's the choreography of existence, a dance we're all part of, whether we're made of stardust or stem cells. Galaxies spin like colossal pinwheels in the void, their arms sweeping through space at hundreds of kilometers per second. At that speed, you'd expect those spirals to wind tighter and tighter over time, like a coiled spring, until the arms merge into a tangled mess. Yet when we look at spiral galaxies billions of years old, their Fibonacci-perfect curves remain pristine, as if time itself paused to admire their symmetry. This cosmic magic trick has a name: density wave theory, the universe's way of preserving spiral arms as enduring masterpieces rather than fleeting brushstrokes. Picture a traffic jam on a circular highway where cars slow down and cluster together before speeding up again. The jam isn't a fixed group of cars, but a moving pattern. Vehicles enter at the back, creep forward, then exit the front while new ones take their place. Spiral arms work the same way. Stars and gas clouds orbit the galaxy's center at different speeds, bunching up in regions where gravity creates a stellar traffic jam. These dense waves move through the galactic disk like ripples in a pond, triggering star formation as they go. The result: brilliant blue young stars illuminate the arms, making the spiral visible, even though the individual stars are always drifting in and out of the pattern. Here's where the Fibonacci connection deepens. These density waves don't just create any spirals, they often settle into logarithmic curves with angles matching the golden ratio. Computer simulations show that when gas clouds compress in the wave, they fragment into clumps spaced at intervals echoing Fibonacci numbers. It's as if the galaxy is solving a gravitational puzzle, and the golden spiral emerges as the most stable solution. Just like a nautilus shell adds chambers without losing its shape, the density wave renews the spiral arms continuously, allowing them to persist for eons without winding up. The proof lies in the stars themselves. Older, yellower stars found between spiral arms reveal the truth. They've drifted away from the wave, while younger, hotter stars blaze along the leading edge. This cycle creates a self-sustaining rhythm. The wave triggers star birth, whose radiation then pushes surrounding gas, reinforcing the wave's structure. The Fibonacci-like spacing between these stellar nurseries isn't random. It's a natural outcome of gravity and angular momentum balancing each other in a cosmic feedback loop. What's truly astonishing is how universal this process is. From the whirlpool galaxy's perfect two-armed spiral to the flocculent twists of galaxies like NGC 2841, the same physics applies. Even galaxies without clear spiral structure, like the Milky Way's neighbor Andromeda, show subtle Fibonacci-inspired asymmetries in their dust lanes, ghostly echoes of density waves shaping matter across billions of years. This timeless dance between chaos and order reveals a profound truth. The universe doesn't just create beauty, it sustains it. The golden ratio in spiral arms isn't a frozen snapshot but a dynamic equilibrium, where stars are born and die while the pattern endures. Like a river that remains a river even as every drop of water flows onward, spiral galaxies preserve their mathematical grace not despite time's passage but because of it, a testament to the enduring power of nature's favorite numbers. If we ever made contact with an alien civilization, how would we begin to communicate? Mathematics might be our universal handshake, a language transcending biology, culture, and even planetary origins. Consider this: the Fibonacci sequence appears in the arrangement of atoms in quasicrystals, the spiral arms of galaxies, and the growth patterns of every ecosystem on Earth. If the laws of physics and the constraints of efficiency hold true across the cosmos, wouldn't an extraterrestrial species also encounter these same mathematical constants? A civilization orbiting a star in the Andromeda galaxy might not share our concept of art or music, but if they've studied the natural world, they've likely seen the golden ratio in the curve of a nebula or the branching of cosmic filaments, just as we have. This idea isn't just speculative fiction. Scientists like Carl Sagan and Stephen Hawking argued that mathematics is the most plausible foundation for interstellar communication. When NASA Pioneer probes carried plaques into deep space, they didn't include words or musical notes. They etched a diagram of hydrogen atoms and geometric patterns, trusting that any advanced species would recognize these universal symbols. The Fibonacci sequence could serve a similar purpose. Imagine transmitting a series of pulses matching the numbers 1, 1, 2, 3, 5, a signal so simple yet so deeply rooted in nature that it might spark recognition across the light years. But here's the tantalizing twist. Aliens might not just recognize these patterns, they could use them. On Earth, architects and engineers employ the golden ratio to create structures that are both strong and efficient. An alien species might construct their megastructures, whether Dyson spheres or orbital habitats, using the same principles, optimizing space and energy with Fibonacci-inspired designs. Even their technology, from propulsion systems to energy grids, could mirror the logarithmic spirals found in galaxies, harnessing the same natural efficiencies that shape hurricanes and Nautilus shells. Of course, not all scientists agree. Some argue that while mathematics is universal, the way cultures interpret patterns could vary wildly. An alien mind might perceive spirals as mere statistical noise, or prioritize entirely different geometric forms based on their planet's unique environment. After all, octopuses, Earth's most alien-like intelligences, see the world through eyes shaped by entirely different evolutionary pressures. Could a silicon-based life form from a tidally locked planet find Fibonacci sequences as compelling as we do? Yet the counterargument is written in the stars themselves. Wherever rotation meets growth, from the quantum foam to galactic superclusters, the universe leans toward these spirals. If aliens have telescopes, they've seen spiral galaxies. If they've studied their own equivalent of seashells or pine cones, they've encountered Philotaxis. The golden ratio isn't just a human obsession. It's a cosmic preference etched into the fabric of reality by the laws of physics. So while we can't know for certain, the odds are intriguing. The Fibonacci sequence might be more than a mathematical curiosity. It could be a beacon, a shared signpost in the vast darkness of space. Whether carved into ancient alien monuments or encoded in interstellar transmissions, these spirals may one day serve as a silent hello between civilizations, a testament to the unity of a universe that speaks in numbers. Hurricanes spin across our planet with the same mesmerizing grace as distant galaxies, their arms coiling into near-perfect logarithmic spirals. Watch satellite footage of a storm like Hurricane Katrina or Dorian, and you'll see those signature curves, not just chaotic whirls, but mathematically precise formations where each band of clouds spirals outward at an angle echoing the golden ratio. This isn't just a visual coincidence, it's physics repeating its favorite recipe. Just as gravity shapes galactic arms, the Coriolis affect Earth's rotation, deflecting moving air sculpts hurricanes into Fibonacci-like spirals, proving efficiency transcends scale. The mechanics are strikingly similar. In a galaxy, stars and gas orbit the center at different speeds, creating density waves that form spiral arms. In a hurricane, air rushes toward the low-pressure eye, then twists upward in towering thunderclouds. The rotation stretches these clouds into spiraling bands, spaced at intervals that often align with ratios found in Fibonacci sequences. Even the storm's eye wall, where winds are fiercest, frequently mirrors the tight, golden ratio proportions of a nautilus shell's inner chambers. Nature isn't just reusing a shape, it's reapplying a universal solution to the problem of organizing rotating systems. But why does this happen? The answer lies in energy optimization. Hurricanes, like galaxies, are engines that convert heat into motion. Warm ocean water fuels them, and the storm's spiral structure allows it to vent excess heat while maintaining stability. The logarithmic spiral offers the perfect balance, tight enough to concentrate energy near the core, yet expansive enough to dissipate turbulence at the edges. This same principle keeps galactic arms from collapsing or flying apart, as gravity and centrifugal force find equilibrium in the golden ratio's embrace. The parallels go deeper than structure. Just as density waves trigger star formation in galactic arms, hurricane spirals birth smaller vortices, mini swirls within the larger storm that meteorologists call mesovortices. These spin off like cosmic eddies, their movements often following the same mathematical rhythms as the parent storm. Even the lifespan of a hurricane echoes galactic processes. Both evolve over time, their spirals tightening or loosening in response to environmental forces, whether interstellar gas or shifting wind shear. Yet hurricanes hold one key difference: they're fleeting. While galaxies maintain their spirals for billions of years, a hurricane might last weeks. This makes them perfect laboratories for studying spiral dynamics in real time. Scientists now use hurricane models to simulate galactic arms, and vice versa, each field informing the other. When researchers tweak variables in a hurricane simulation, changing sea temperatures or wind speeds, the resulting spiral adjustments mirror what astrophysicists see when they alter a galaxy's gas density or rotation rate in computer models. This convergence of meteorology and astronomy hints at something profound. Whether you're looking at a storm from space or a galaxy through a telescope, you're witnessing the same cosmic choreography. The Fibonacci sequence isn't confined to shells and sunflowers. It's written in the whirl of a tornado, the swirl of a galaxy, even the spiral of cream in your coffee. Physics has a limited playbook, and when rotation meets growth, the golden spiral emerges as nature's favorite blueprint, stitching the universe together from the smallest vortex to the grandest cosmic design. While the Fibonacci sequence paints a stunning picture of cosmic order, the universe loves to surprise us. Not every spiral galaxy adheres to this mathematical script with textbook precision. Take the stunning pinwheel galaxy Messier 101. Its arms burst outward in a dazzling but slightly chaotic display, more like a child's pinwheel spinning in the wind than the tight, golden ratio spirals of the Whirlpool Galaxy. Then there's NGC 1300, the topsy-turvy galaxy, where one arm stretches gracefully while the other appears shredded, as if cosmic turbulence interrupted nature's blueprint mid-sketch. These outliers aren't failures of design, they're reminders that the universe balances mathematical elegance with glorious unpredictability. What causes these deviations? Often, it's the messy business of cosmic evolution. Galaxies don't exist in isolation, they collide, merge, and tug at each other gravitationally. The antennae galaxies, for example, are a pair locked in a slow-motion dance of destruction, their once neat spirals now stretched into long, streaming tails of stars. Even solitary galaxies can develop asymmetries when supernovae explode or when their central black holes belch jets of energy, disrupting the delicate balance of their spiral arms. These galactic imperfections reveal a deeper truth. The Fibonacci sequence isn't a rigid mold but a guiding tendency, a starting point from which real-world physics adds its own improvisations. Some galaxies defy the spiral archetype altogether. Flocculent spirals like NGC 2841 resemble tufts of cotton candy, their arms fragmented and patchy rather than continuous. Others, like Hoag's object, present as near-perfect rings with almost no spiral structure at all. Yet even in these exceptions, traces of mathematical order persist. The star-forming regions in flocculent galaxies often cluster at intervals that approximate Fibonacci numbers, while ring galaxies can exhibit subtle logarithmic spacing in their radial features. It's as if the universe defaults to these ratios when possible, but isn't shackled by them, a flexible artist rather than a strict engineer. This nuance matters because it mirrors how Fibonacci patterns appear on Earth. Not every sunflower has exactly 34 and 55 spirals. Some might skew to 21 and 34 under environmental stress. Pinecones can vary their scale arrangements based on nutrient availability. The sequence isn't a law but a probability, a statistical favorite that emerges when conditions allow. In galaxies, those conditions include stable rotation, balanced gravity, and minimal disruptions. When outside forces intervene, the perfect spiral may warp, but the underlying mathematics never fully disappears, it adapts. These exceptions don't weaken the Fibonacci galaxy connection, they enrich it. Just as jazz musicians play with rhythm while staying rooted in musical theory, galaxies riff on mathematical themes while embracing cosmic chaos. The beauty lies in the interplay, the way a galaxy like Messier 81 can flaunt nearly perfect golden ratio arms while its neighbor, Messier 82, bristles with ragged, star-forming fury. Both are valid expressions of the universe's creativity, one polished and precise, the other wild and untamed. Together, they remind us that nature's patterns are a language, not a prison, a vocabulary of shapes that the cosmos arranges and rearranges in infinite variation. The universe has shown us its fondness for Fibonacci spirals, from galaxies to sunflowers, but the why behind this mathematical obsession remains one of science's most tantalizing puzzles. While we've uncovered countless examples of these patterns across scales, the underlying mechanisms that make them so universal are still being unraveled. One leading theory suggests it's all about optimization, whether it's a plant packing seeds or a galaxy organizing stars. The Fibonacci spiral offers the most efficient way to balance growth and stability. But is efficiency alone enough to explain why this sequence emerges in such wildly different contexts, from quantum materials to galactic arms? Or is there something deeper, a fundamental principle woven into the fabric of spacetime itself that favors these ratios. This is where cutting-edge astronomy comes in. Telescopes like the James Webb Space Telescope, with its unprecedented infrared vision, are peering into the hearts of distant galaxies, studying the birth of stars within their spiral arms with razor-sharp detail. By analyzing the precise angles of these arms and the spacing of star-forming regions, researchers hope to catch the universe in the act of calculating its Fibonacci patterns. Early observations of young galaxies, those forming just a few 100 million years after the Big Bang, could reveal whether these spirals appear fully formed or emerge gradually, offering clues about whether the golden ratio is baked into cosmic evolution from the start. Meanwhile, physicists are running ultra-precise simulations on supercomputers, tweaking variables like dark matter distribution and gas turbulence to see how spiral structures respond. Some models suggest that Fibonacci-like patterns might be inevitable in any rotating system where gravity competes with centrifugal force, whether it's a protoplanetary disk or a galaxy cluster. Others speculate that quantum effects, like entanglement or spacetime fluctuations at microscopic scales, might scale up to influence galactic morphology. Could the same quantum rules that arrange atoms in a quasicrystal also nudge stars into golden ratio spirals? It's a radical idea, but one that future observatories, like the upcoming Vera C. Rubin Observatory, might test by mapping billions of galaxies for subtle mathematical fingerprints. Then there's the biological angle. Astrobiologists are fascinated by the possibility that Fibonacci patterns could be a universal signature of life itself. If alien ecosystems on distant exoplanets also exhibit Philotaxis spiral growth patterns in plants or microbes, it would suggest that the sequence is a cosmic constant, not just an earthly quirk. Missions like the Habitable Worlds Observatory, set to launch in the next decade, might one day spot Fibonacci forests on distant worlds by analyzing the light reflected off their surfaces for telltale mathematical regularities. Yet for all our tools and theories, the biggest questions linger. Why does the golden ratio feel so inherently pleasing to humans, from art to architecture? Is our perception of its beauty a cultural construct? Or does it reflect something primal, a neural wiring shaped by eons of evolution in a Fibonacci-patterned world? And if we ever encounter extraterrestrial intelligences, would they share this aesthetic instinct, or would their mathematical taste be entirely alien? The more we learn, the clearer it becomes. The Fibonacci sequence isn't just a curious pattern. It's a bridge between disciplines, a thread connecting cosmology, biology, and even consciousness. With every discovery, we're not just decoding the universe's blueprint, we're learning how deeply we're woven into it. Want to witness the universe's mathematical artistry for yourself? Grab a telescope and point it toward the Whirlpool Galaxy, also known as Messier 51. Even through amateur equipment, those iconic spiral arms reveal their logarithmic curves, each one a swirling testament to the Fibonacci sequence's cosmic reach. Start with a low-power eyepiece to take in the galaxy's grand design, then zoom in to trace the arms as they unwind from the glowing core. Notice how the spacing between star clusters and dust lanes isn't random. It follows the same rhythmic progression you'd find in a pinecone scales or a nautilus shell's chambers. This isn't just stargazing, it's a front-row seat to nature's universal blueprint. For beginners, the Pinwheel Galaxy, Messier 101, offers another dazzling target. Its face-on orientation makes its Fibonacci-inspired spirals easier to spot, especially under dark skies. Use a star chart to locate it near the handle of the Big Dipper, and you'll see why astronomers call it a grand design spiral. The arms aren't just pretty, their curvature often matches the golden angle, roughly 137.5 degrees, the same mathematical sweet spot that arranges petals around a rose's center. With a camera attached to your telescope, even short exposures can capture these patterns, transforming abstract math into tangible light. But you don't need high-tech gear to join the hunt. Binoculars under a moonless sky can reveal the Andromeda Galaxy's subtle spiral structure, its dust lanes tracing faint Fibonacci-like arcs. Apps like Stellarium or Sky Safari can guide you to these cosmic masterpieces, overlaying real-time star maps with galaxy orientations. Pay attention to how these spirals compare. Some, like Messier 81, boast tight, textbook-perfect golden ratios, while others, like NGC 2841, flaunt looser, fragmented arms. These variations aren't flaws, they're cosmic experiments in how rotation and gravity negotiate their eternal dance. The thrill lies in the connection. When you sketch what you see through the eyepiece, you're not just drawing a galaxy, you're retracing the same mathematical rhythms that guided Da Vinci's sketches and ancient temple builders' blueprints. Astrophotographers often enhance this link by superimposing Fibonacci spirals over their images, revealing how closely cosmic and earthly patterns align. It's a humbling reminder that the same forces shaping a sunflower's seeds also sculpted the Whirlpool Galaxy's arms, a truth visible anytime you train your telescope on the night sky's swirling wonders. The Fibonacci sequence's fingerprints on everything from galaxies to seashells raise a profound question. Is mathematics merely a human invention to describe the universe, or is it the universe's native language? Ancient philosophers like Pythagoras believed numbers were divine, the hidden scaffolding of reality itself. When we find the same spiral in a hurricane, a Nautilus shell, and a galaxy billions of light years away, it's hard not to wonder if these patterns hint at something deeper. A cosmos where beauty and function aren't just aligned but fundamentally intertwined. Consider the golden ratio's uncanny resonance across disciplines. Artists like Da Vinci and composers like Debussy wove it into their work because it felt harmonious, long before science confirmed its prevalence in nature. Physicists now find it in quantum materials and black hole dynamics, while biologists trace it in DNA helices and branching neurons. This convergence suggests the sequence isn't just a handy tool, it might be a cosmic constant, a preferential pathway etched into the laws of physics. Like gravity or light speed, the golden ratio could be less a discovery than an inevitability, waiting to emerge wherever growth meets rotation or structure meets flow. Yet not all scholars agree. Skeptics argue that Fibonacci patterns are simply the most efficient solutions to universal problems, packing seeds, organizing stars, or dissipating energy, making their recurrence a statistical likelihood rather than mystical design. In this view, the sequence is nature's favorite shortcut, not its blueprint, but even this pragmatic perspective can't fully explain why these ratios feel transcendent. When Hubble images of spiral galaxies evoke the same awe as a cathedral's arches, it challenges the boundary between science and art, logic and wonder. Perhaps the truth lies between these poles. The Fibonacci sequence might be neither accidental nor divine, but something even more remarkable, evidence of a universe that self-organizes according to simple, elegant rules. Every spiral arm, every branching tree, every vibrating quantum field could be participating in a grand, iterative process, one that balances chaos and order through mathematics we're only beginning to decode. In that sense, the sequence isn't just describing reality, it's revealing how reality computes itself from the smallest scales to the largest. This duality, math as both tool and essence, resonates with modern theories like pancomputationalism, which posits that the universe literally processes information. If spacetime is a kind of cosmic processor, the Fibonacci sequence could be its algorithm for creating stable, evolving structures. From quasi-crystals to galactic arms, these patterns might represent nature's way of optimizing energy, matter, and even time itself. Ultimately, the sequence's ubiquity invites us to rethink our place in the cosmos. We aren't just observers of these patterns, we're products of them, our bodies, our art, even our perception of beauty shaped by the same mathematics that whirls stars into spirals. Whether you see it as coincidence, necessity, or something transcendent, one thing is clear: the universe speaks in numbers, and the Fibonacci sequence is one of its most poetic dialects. For millennia, the spiral has whispered to humanity's deepest yearnings, a sacred symbol etched into ancient petroglyphs, carved into temple pillars, and woven through creation myths across cultures. The Maori saw it in the unfurling fern frond, a metaphor for life's cyclical journey. Celtic artisans coiled it into intricate knotwork, representing eternal rebirth. And when modern seekers gaze upon Hubble's images of Fibonacci-perfect galaxies, many feel the same awe, not just at the mathematics, but at the uncanny sense that these celestial patterns are more than cosmic accidents. They're signatures of something transcendent, a hidden order that bridges the physical and the metaphysical. Consider the mandala, a spiritual symbol across Hinduism and Buddhism. These intricate circular designs often incorporate logarithmic spirals, guiding meditation from outer chaos to inner stillness. The journey inward mirrors the path of a galaxy's arms, both drawing energy toward a center, both balancing expansion and return. Tibetan monks painstakingly craft sand mandalas only to sweep them away, a reminder of impermanence. Yet the spirals in those mandalas echo the same timeless geometry that shapes galaxies persisting for billions of years. Is this convergence mere coincidence, or does it hint at a deeper harmony between microcosm and macrocosm? Even the golden ratio, so prevalent in Fibonacci spirals, has long been shrouded in mysticism. The 12th century mathematician Fibonacci encountered the sequence while studying rabbit populations, but its roots stretch back further. Ancient Egyptians encoded it in the Great Pyramid's dimensions, aligning its slopes with celestial cycles. Plato called the golden ratio the key to the physics of the cosmos, while Renaissance polymaths like Kepler saw it as divine geometry, a celestial fingerprint. Today, spiritual thinkers propose that galaxies, with their golden ratio arms, are physical manifestations of what mystics describe as the sacred spiral, a path of evolution, both personal and universal. This perspective isn't confined to esoteric traditions. Modern physicists flirting with theories of consciousness point to the Fibonacci sequence's ubiquity as potential evidence of a participatory universe. If subatomic particles exhibit wave-like behavior only when observed, could the very act of perceiving galactic spirals somehow resonate with their structure? It's a radical idea, but one that finds echoes in indigenous cosmologies. The Hopi people, for instance, speak of the road of life as a double spiral, one path representing physical growth, the other spiritual awakening, mirroring the dual arms of galaxies like Messier 81. Yet skepticism tempers these interpretations. Scientists caution against conflating mathematical beauty with intentional design. The golden ratio's prevalence, they argue, stems from efficiency, not divinity, a natural outcome of systems optimizing space and energy. But even this pragmatic view holds a kind of poetry. If the universe chooses Fibonacci spirals because they work, doesn't that still suggest an inherent intelligence to physical laws? Perhaps the divide between spiritual and scientific awe is narrower than it seems. Both perspectives, after all, grapple with the same breathtaking truth. that from the quantum foam to galactic superclusters, the cosmos hums with patterns that feel, in some profound way, meant to be seen. Whether you view these spirals as sacred geometry or stellar mechanics, their power to stir wonder remains undeniable. They invite us to consider our place in a universe where a single mathematical thread connects the curl of a breaking wave, the whirl of a dervish's dance, and the slow turn of a galaxy's arms across the eons. In that sense, the Fibonacci sequence becomes more than a formula. It's a mirror, reflecting back our eternal quest to find meaning in the stars. Imagine a classroom where students lean forward, eyes wide, as their teacher projects an image of the whirlpool galaxy onto the screen. Instead of dry equations on a chalkboard, they're tracing the galaxy's swirling arms with their fingers, counting the logarithmic curves that match the Fibonacci sequence they just learned about in math class. This is the power of cosmic pedagogy, using the universe's grand designs to transform abstract numbers into tangible wonder. Educators from elementary schools to universities are discovering that galactic spirals aren't just celestial phenomena. They're the ultimate teaching tools, bridging the gap between algebra and awe. Take M.S. Rodriguez's 6th grade class in Texas, where a lesson on number sequences begins not with a textbook but with sunflowers and galaxies side by side. Students measure the spirals in sunflower seed heads, tallying clockwise and counterclockwise curves to find consecutive Fibonacci numbers 21 and 34, or 34 and 55. Then they flip to a Hubble image of Messier 74, a galaxy whose arms unfurl with the same mathematical precision. The revelation is electric. Wait, math isn't just something we do for homework, it's written in the stars. Exclaims one student. This interdisciplinary aha moment is exactly why NASA Education Office partners with schools to develop astronomy-based math curricula, proving that when equations escape the page and dance across the cosmos, even reluctant learners lean in. But the magic isn't just in the visuals, it's in the hands-on activities that follow. In a high school geometry class in Norway, students use 3D modeling software to recreate galactic spirals, inputting Fibonacci ratios to generate curves that mirror nature's designs. They tweak variables like rotational velocity and gas density, watching as their digital galaxies morph from chaotic blobs into graceful spirals, a visceral lesson in how mathematical constants shape reality. Meanwhile, in Japan, a university astrophysics professor assigns students to photograph Fibonacci patterns in their daily lives: pine cones, storm clouds, even the curl of their own hair, then compare them to images from the Subaru telescope. The assignment isn't just about observation, it's about recognizing the universe's repetitive vocabulary, a language spoken from microscopic to galactic scales. The ripple effects of this approach extend beyond test scores. A 2023 study published in the Journal of Astronomy Education tracked students engaged in galaxy-based math programs and found a 40% increase in sustained interest in STEM fields compared to traditional methods. One 8th grader put it plainly, "When I saw that the same math in my doodles was in a galaxy millions of light years away, I realized maybe I'm not bad at math. Maybe math was just waiting to blow my mind." Teachers report deeper classroom discussions too, like debating whether the golden ratio in galaxies suggests a cosmic aesthetic or purely functional origins, fostering critical thinking alongside calculation skills. Yet the most profound impact might be cultural. In indigenous communities from New Zealand to Arizona, educators are weaving traditional star knowledge with Western mathematics. Maori students learn about the Fibonacci sequence through the koru, a spiral shape symbolizing growth in their art. then connected to both galaxy arms and ancestral navigation techniques that guided Polynesian voyagers across the Pacific. This fusion of worldviews doesn't just make math relatable. It restores a sense of unity to knowledge, reminding students that the patterns overhead are the same ones their ancestors studied millennia ago. From planetarium workshops where kids build galaxies with glitter and glue to university labs where physics majors simulate dark matter's influence on spiral structure, these educational experiments share a common truth. The universe is the most captivating textbook ever written. When a teenager realizes that the math behind their favorite galaxy's swirl also designs their playlist's most harmonious melodies or the smartphone in their pocket, it doesn't just teach them about numbers. It teaches them that they're part of a cosmos far more interconnected and far more wondrous than they ever imagined. The same spiral that shapes galaxies and sunflowers now guides human hands in crafting the technology that propels us into the future. Consider solar arrays in space, those gleaming wings of satellites that unfurl to catch sunlight. Engineers arrange their photovoltaic cells in Fibonacci-inspired spirals, not for beauty alone, but because this centuries-old pattern maximizes surface area while minimizing weight, just as it does for leaves capturing sunlight on Earth. When NASA Juno spacecraft spread its solar panels wide enough to span a basketball court, their segmented design followed logarithmic spacing to balance structural integrity with energy absorption, proving that nature's blueprints work just as well in the vacuum of space as they do in a forest canopy. Architects have long borrowed this mathematical wisdom, but today's pioneers push it further. The Shanghai Tower, China's twisting skyscraper, spirals skyward at a golden ratio angle, reducing wind resistance by 30% compared to straight-edged towers. Its curves aren't just an aesthetic flourish, they mimic the hurricane spirals we see from orbit, where fluid dynamics naturally adopt Fibonacci-like forms to dissipate energy. Even earthquake-resistant buildings now incorporate base isolators shaped like nautilus shells, their logarithmic coils absorbing seismic shocks more efficiently than traditional springs. It's as if we've learned to speak nature's language of resilience, translating cosmic patterns into urban survival. The tech world whispers this secret too. Your smartphone's antenna likely follows a Fibonacci spiral layout, packing more signal range into limited space, an innovation inspired by how galaxies efficiently arrange stars along their arms. Computer chips employ golden ratio spacing in their circuits to reduce electromagnetic interference, a trick borrowed from the evenly spaced florets of a cauliflower. Even 3D printers now use algorithms based on Fibonacci sequences to build lightweight yet ultra-strong structures, layer by layer, just as coral constructs its skeleton using the same mathematical rules. Perhaps the most poetic fusion emerges in renewable energy. Wind turbine companies like Vestas design blades with curvature ratios matching sunflower spirals, boosting efficiency by harmonizing with airflows that already follow these ancient rules. Underwater, tidal power generators mimic the Fibonacci spacing of kelp forests to minimize turbulent drag while capturing maximum kinetic energy. These aren't just engineering solutions, they're collaborations with the universe, acknowledging that 4 billion years of planetary trial and error have already refined the best designs. Yet the most profound applications might be those we can't yet see. Quantum computing researchers are experimenting with quasi-crystals, those Fibonacci-ordered materials, to create error-resistant processors. Early prototypes suggest their non-repeating but mathematically perfect structures could outperform conventional silicon chips, much like how a galaxy's spiral arms maintain stability where random star clusters would collapse. From nanoscale circuits to spacefaring megastructures, humanity is learning to think in spirals, discovering that the universe's favorite equation might also be its most versatile tool. This convergence of biology, physics, and human ingenuity reveals a humbling truth. The most advanced civilizations may not be those that conquer nature, but those that listen to it. When a solar panel mirrors a leaf or a skyscraper echoes a hurricane, we're not just borrowing shapes, we're tapping into a universal principle written into the fabric of reality itself. The golden ratio isn't merely a design trend. It's a bridge between the cosmos and the creations we hope will one day reach it. It's tempting to see the Fibonacci sequence everywhere, to gaze at a galaxy's spiral or a hurricane's whirl and assume it's another flawless example of nature's golden ratio. But science thrives on skepticism, not just wonder. For every whirlpool galaxy with its textbook-perfect arms, there's a NGC 4321, a messy, asymmetrical spiral that defies easy classification. The truth is, while Fibonacci patterns are undeniably common, they're not universal. Recognizing where they don't fit is just as crucial as celebrating where they do. Take the so-called grand design spirals like Messier 81, where the arms gleam with mathematical precision. Contrast that with flocculent galaxies, those cosmic cotton balls like NGC 2841, where star-forming regions scatter like dandelion fluff, their spirals fragmented and irregular. These galaxies aren't failed Fibonacci examples. They're proof that other forces, turbulence, collisions, or uneven gas distribution, can override nature's preference for golden ratios. Even in our own Milky Way, the spiral structure isn't perfectly symmetrical. One arm may stretch longer, another kink abruptly, as if the galaxy itself is still working out the kinks in its design. This isn't unique to space. On Earth, pine cones and sunflowers often follow Fibonacci numbers, but not always. Environmental stress, genetic mutations, or resource scarcity can skew their patterns. A drought-stricken sunflower might produce 21 and 33 spirals instead of the classic 21 and 34. These outliers aren't mistakes. They're reminders that biology negotiates with math, never rigidly obeying it. The same applies to hurricanes. While many storms mirror logarithmic spirals, some, especially those influenced by wind shear or land interaction, twist into lopsided, chaotic shapes that no Fibonacci formula could predict. Why does this matter? Because mistaking coincidence for pattern is how myths take root. The Fibonacci fallacy crops up in pop science all the time. Claims that the Great Pyramid's dimensions or Da Vinci's Vitruvian Man adhere perfectly to the golden ratio often crumble under scrutiny. Measurements can be cherry-picked, ratios exaggerated. Even galaxies get mislabeled. Hoag's object, that enigmatic ring galaxy, is sometimes falsely cited as a golden ratio masterpiece, despite its structure owing more to gravitational quirks than mathematical harmony. Critical thinking is the antidote. When astronomers analyze spiral arms, they don't just marvel at their curves. They model the physics, gravity, angular momentum, gas density. Sometimes the numbers align with Fibonacci, often they don't. That's the beauty of science. It embraces the messy reality, not just the elegant theory. So while the universe clearly loves a good spiral, it's not enslaved to one script. Its creativity is boundless, weaving order and chaos into designs we're only beginning to decode. From the tiniest whirl of a subatomic particle to the vast, sweeping arms of a galaxy 100,000 light-years across, the Fibonacci sequence whispers its quiet truth that the universe adores a spiral. This isn't just about numbers on a page. It's the revelation that mathematics is the silent architect of reality, shaping everything from the curl of your morning coffee steam to the way stars pirouette around the hearts of galaxies. The deeper we look, the clearer it becomes. Elegance and efficiency aren't accidents. They're the universe's way of solving problems, whether it's a sunflower packing seeds or a black hole sculpting starlight into logarithmic curves. What's truly humbling is realizing we're part of this pattern too. The cochlea in your ear, the branching of your lungs, even the way your neurons fire, all carry faint echoes of the same spirals etched into the night sky. We don't just observe the Fibonacci sequence, we're woven from it, living proof that the cosmos repeats its favorite designs across scales. And that's the magic of this journey. It's not just about decoding galaxies or admiring seashells. It's about recognizing that we're participants in a grand mathematical dance, one that's been unfolding since the first stars ignited. But here's the best part, the mystery isn't solved. Every time a telescope captures a new spiral galaxy or a biologist finds Fibonacci numbers in an unexpected leaf, the universe winks, reminding us there's more to discover. Maybe you've noticed these spirals in your own backyard, the way succulents arrange their leaves or how storm clouds coil before a summer rain. That's the invitation this pattern extends, to stay curious, to keep looking closer. Because the moment we think we've unraveled all its secrets, the cosmos will surprise us with a spiral we never saw coming. So grab a pair of binoculars, a sketchbook, or just your sense of wonder. The Fibonacci sequence isn't locked away in textbooks, it's alive, spinning through the world around you and the stars above. And if you've ever felt small under the night sky, remember, you're not separate from the grand design. You're a vital stitch in its fabric, a witness to its beauty, and maybe, just maybe, the one who'll help decode its next great secret. The universe has been leaving clues for billions of years. Who's to say the next breakthrough won't